Welcome to the 30th lecture of this open course on diffusion in multi-component solids. In this lecture, I will explain some of the important mechanisms of diffusion in metallic alloys. These include interstitial diffusion and vacancy diffusion mechanisms. I will also briefly describe direct exchange and ring mechanisms. Expressions are also derived for diffusivity of atom by vacancy and interstitial mechanisms. Now that we have gone through energetics of the point defects, we will look into some of the mechanisms of diffusion. This lecture we will look into the mechanisms of diffusion specifically in crystalline metals and alloys. So, to start with, the first diffusion mechanism is interstitial diffusion. We know that if the size of the solute atom is very small, smaller than the parent atom, then it can occupy the interstices between the regular atomic positions. Those are called interstitials. The interstitial atoms are also vibrating about their mean position, and if a particular vibration has an energy greater than that required to jump onto the next interstitial site, then it can actually jump onto the next interstitial site. So, this diffusion from one interstitial site to the next interstitial site is referred to as interstitial diffusion, or we say that the solute atom is diffusing by interstitial mechanism. An example of interstitial diffusion is the diffusion of carbon in steel. In both BCC and FCC ion, carbon occupies the interstitial sites and it diffuses by interstitial mechanism. So, if we can visualize the interstitial sites in FCC and BCC, let us first look into FCC. There are two types of interstitial sites, octahedral and tetrahedral. First look into the octahedral interstitial site in FCC crystal. Octahedron is a figure having 8 faces. So, octahedral interstitial site lies at the center of a octahedron, which you can draw with the regular atoms of the lattice site at its corner of the octahedron. So, if we can draw an octahedron in FCC lattice, consider the 4 face centered atoms of the vertical faces and the 2 face centered atom of the horizontal faces, and if you join these atoms, they will form an octahedron. And the center of the octahedron lies at the center of the unit cell, the body center of the unit cell. Okay. So, this is one octahedral site. Similarly, you can show that other octahedral sites lie at the centers of the edges of this FCC unit cell, right. So, the octahedral sites in FCC are 1 body center position and others are at the edge centers. Since each edge is shared by 4 unit cells, only 1/4 of the octahedral interstitial site on the edge lies inside a unit cell. So, there are total 12 by 4, which is 3 plus 1 at the body center. So, there are total 4 octahedral site per unit cell in a FCC crystal. So, if we try to visualize these atoms, if we can draw this plane formed by these atoms, let us label it as A, B, C and D. So, this is A, B, C, D. So, this is my A, B, C and D. So, A, B, B, C, C, D and D A, they are touching each other, because they are the nearest neighbor, and obviously there will be one atom on top. So, this is this atom E, and there will be one atom at the bottom. Let us call this F, and these atoms will form a octahedron, and interstitial or the void that is at the center of this is the octahedral interstitial site. So, if an atom sits in this octahedral interstitial position, there will be another interstitial position somewhere here, and as the atom jumps interstitially from this position to the next position, it has to cross an activation barrier, which means in between there will be a state as the atom moves from one interstitial position to the other. In between there will be a state which is characterized by a maximum in the energy. Since these two are the equilibrium positions, so there will be a minimum, there will be a maximum somewhere in between. So, this is I am drawing energy versus the distance. This is the x coordinate. This first position is at minimum, second position is at minimum, and there will be a maximum in between. And this maximum position corresponds to what we call as saddle configuration. Now, you can imagine as the atom is moving from this one side into the other, these two atoms C and D have to be pulled apart, so that there is an enough space for this interstitial atom to pass through, and that is the saddle configuration. So, on its way to the next interstitial site, if we draw this configuration, it will be something like this. The X atom is exactly between the two positions C and D. So, this is the saddle configuration or the configuration corresponding to maximum in the energy, and this difference is called the Gibbs free energy of migration. The difference between the Gibbs free energies of the two configurations, this equilibrium configuration and this saddle configuration, is called the Gibbs free energy of migration, or that is the barrier which exists for this interstitial atom to diffuse from one site into the other. That we call as activation energy for migration of the atom. Similarly, there will be tetrahedral interstitial sites in FCC, those lie along the body diagonals. So, if we consider any three adjacent face center atoms and the corner atom which all the three face center atoms touch, then we can draw a tetrahedron, meaning a figure having 4 faces, and the center of the tetrahedron we can see will lie along the body diagonal. Precisely, it will be at a position which is at 1/4 of the body diagonal length. By symmetry, you can show there will be another interstitial at 3/4 of the body diagonal, and there are 4 such body diagonals. So, there will be total 8 tetrahedral sites in a FCC unit cell. So, this is tetrahedral in FCC. Can also show octahedral in BCC. To show octahedral in BCC, we can consider the body center of this unit cell and the body center atom of a unit cell which lies on top of this one, and join those to the 4 corner atoms which lie in between them. If you join this, you can form an octahedron, and the center of this octahedron lies exactly at the center of the face. Similarly, there will be other octahedral positions at the center of the edges. So, the octahedral sites in BCC are on the centers of the faces and centers of the edges. For tetrahedral sites in BCC, let us consider the 2 body center atoms, one at the body center of this unit cell which is drawn, and the one at the body center of the unit cell which is on top of this one. Consider the 2 side corner atoms in between them, and you can join them to form a tetrahedron. And the center of this tetrahedron lies somewhere on the face, and its position is at 1/4 of the lattice parameter from the center of the edge. Right. So, if we draw this face here, the tetrahedral interstitial sites are located at 1/4 from the center of each of the edge. Okay. So, these are the octahedral interstitial sites in FCC and BCC, and the interstitial atom diffuse by jumping from one interstitial site into the next interstitial site, and this is the interstitial mechanism of diffusion. Now, the next mechanism that we are going to look at is by vacancy. As we have seen in previous lectures, at any given temperature above 0 Kelvin, there is an equilibrium concentration of vacancies in any crystalline solid. which means at any given temperature there exists certain number of vacant sites in a crystalline solid. So, a regular atom which is vibrating about its mean position, if it gains enough energy, it can jump into the next site if it is vacant. This is also equivalent to the vacant site making a jump into in a reverse direction. This is the diffusion by vacancy mechanism. The hopping of atom from one regular lattice site onto the next lattice site is mediated by vacancy, and this is the vacancy mechanism of diffusion. So, if we look this particular jumps, if we try to visualize these particular jumps in an FCC lattice, so if we look at particularly at 111 plane, so this is how the atoms are arranged in a 111 plane. Each atom is surrounded by 6 nearest neighbor atoms within plane, and there will be 6 out of plane. So, 3 of them will be on top, 3 of them will be at the bottom of this plane, and the way we can place those atoms are, if we join these atoms in the hexagonal arrangement, then there will be 6 triangles, 3 pointing up and 3 pointing down. So, if we place dots at the center of the triangles which are pointing up and cross at the center of the triangles which are pointing downwards. So, these are the 6 positions out of plane, or the 6 nearest neighbor out of planes. So, these cross are the 3 nearest neighbor atoms of this central one, which are lying in the plane below this plane, and the dots are the 3 nearest neighbor atoms of this central atom which are on top of this plane. So, 6 plus 6, there are 12 nearest neighbor, and the vacancy diffusion most probably takes place by nearest neighbor jumps. So, this central atom has 12 possible sites onto which it can jump, if a particular site happens to be vacant site. And what would be the jump length? So, this central atom, there are 12 nearest neighbor. So, the jump distance, that is the distance between the nearest neighbor atoms. So, if we mark this length, how much it would be? We can figure it out. So, it will be essentially any face center atom moving on to the corner site is one nearest neighbor jump, and we can see it is half the face diagonal. So, the jump length, which is as alpha, is half the face diagonal, and what would be the length of the face diagonal? If we denote each edge as A, the lattice parameter, and the face diagonal length as x, then we know x square is equal to a square plus a square, and so x is equal to root 2a, and the jump length in FCC by vacancy mechanism would be half the phase diagonal, which is half root 2 a, that is a by root 2. Where will be the saddle point? If we draw this again, if this atom A at the center has to diffuse onto the next site, let us denote this by V, which is vacant. We can see that these two atoms have to be pushed apart. Similarly, there is one atom on top and one atom at the bottom, which also have to be pulled apart. So, the saddle point would be somewhere in between. So, if you draw the energy versus distance, you can see there will be a maximum at the saddle configuration, and the difference between the Gibbs free energy of the two states, the equilibrium state and the saddle configuration, is the delta G m, or Gibbs free energy of migration of this atom A. This jump of A into vacancy is equivalent to the reverse jump of vacancy into the site A, and both the diffusion of A by vacancy mechanism or the diffusion of vacancy would have the same energy of migration, delta G m. Then in BCC, what would be the jump length? In BCC, there are 8 nearest neighbor to any particular regular atom position. So, to show the nearest neighbor, consider the body center atom, and all the 8 corner atoms are the nearest neighbors. So, the jump length is typically half the, you can see it is half the body diagonal, right. So, the jump length in BCC would be half the body diagonal, and the body diagonal, the length of body diagonal you can evaluate. This is the face diagonal, which is root 2 a, and this is edge, which is length a. If so, if y is the body diagonal length, then it would be, you can see y square is equal to a square plus 2 a square. So, y is equal to root 3 a. So, the jump length for BCC would be root 3 a by 2. Now, the saddle point configuration for BCC would be a little more complicated. To visualize that saddle point configuration, let us draw 2 interpenetrating BCC unit cells. This is the first unit cell, and the second one drawn with body center of this unit cell being one of the corners of this. So, if this body center atom has to jump onto one of its nearest neighbor, let us say the one on this corner, this is atom A, let us say there is a vacancy here, it has to pass through two saddle points, that is it on its way from A to V, the atom will encounter two states in which there is a maximum in the Gibbs free energy. So, the first state is at the center of the triangle formed by these three atoms. And the second saddle point is at the center of the triangle formed by these three atoms. So, if we draw the energy versus distance as the atom moves from position A to position V, there will be two positions where the energy will be maximum. Of course, A and V are the equilibrium positions. So, there will be, so the energy there will be minimum. You see there will be two states in between where the energy will be maximum. And so, there are two saddle points. So, this is the double saddle configuration in BCC. Okay. So, now let us try to find the expression for diffusivity by the vacancy mechanism. In a previous class, we derived the expression for diffusivity for any cubic lattice, which was d is equal to 1/6 gamma alpha square, right, in which alpha is the jump length and gamma is the successful jump frequency. By knowing the lattice parameter, we can know the jump length for a particular type of lattice, FCC, BCC, etc. For the successful jump frequency, this is the number of jumps which are successful per second. A successful jump is the one in which atom jumps from one regular site onto the nearest neighbor vacant site. So, in order to evaluate the successful jump frequency in terms of the vibrational frequency of an atom, we can write is equal to the total number of vibrations of the atom per second times the probability that a particular vibration becomes a successful jump. Each vibration of an atom, we can consider it as an attempt to jump onto the next site, right. So, the total number of vibrations is the total number of attempts that the atom makes per second to jump onto the next site, and it will be equal to nu 0, the Debye frequency, which is roughly constant at 10 to power 13. And what is the probability that a particular vibration will be successful? For the jump to be successful, there are two conditions. First, the atom has to acquire an energy equal to or greater than the migration energy delta Gm and second, at the same time the next site has to be vacant, that is there has to be a vacancy in the next site. So, the probability that the atom has an energy equal to or greater than delta G m is exponential minus delta G m by R t. And what is the probability that a particular site is a vacant site? It will be total number of vacancies divided by the total number of lattice sites, that is the site fraction of vacancies, or what we denote as x 1 v, right. And x 1 v we know is equal to exponential minus delta G 1 v by R t. So, if we substitute back into this, we get gamma equal to mu 0 exponential. Now, if we write delta G as delta H minus T delta S, and then if we take the entropy and enthalpy terms together, we can write mu 0 exponential delta S m plus delta S 1 v vibrational divided by R times exponential minus delta H m plus delta H 1 v divided by R t. Here delta H m is the enthalpy of migration and delta H 1 v is the enthalpy of mono vacancy formation. Delta S m is the entropy of migration, or it is the difference between the entropy of the equilibrium state and the saddle point, and delta S 1 v is the vibrational entropy change due to formation of a mono vacancy. We substitute into the expression for D, it becomes 1/6 mu 0 alpha square. This combinedly we can denote as entropy of diffusion, and this combined we can denote as enthalpy of diffusion, or the energy barrier for diffusion, which is denoted as Q d. Now, this term is typically relatively independent of temperature compared to this term. The second term, the exponential term, this has an exponential dependence on temperature, and these are typically combined in one parameter, which is denoted as d 0. So, we get an expression for d as d 0 exponential minus q d by R t. Q d is called the activation energy for diffusion, and from here we know that it has two contributions. One, because of the activation energy for migration of the atom, and the second from energy for mono vacancy formation. Right, this we denoted as delta H m, and this part we denoted as delta H 1 v. This is for the diffusion of the atom by vacancy mechanism. The two types of diffusion that take place by this mechanism are self diffusion and substitutional diffusion. Self diffusion means diffusion of an atom in its own crystal, and the substitutional diffusion refers to diffusion of a solute atom by the vacancy mechanism. Typically, if the solute atom is large in size, it cannot occupy any interstitial position. So, it will occupy the regular atomic sites in the parent lattice. So, we refer to it as the solute atom substitutes the parent atom. So, it is called the substitutional atom, and such a substitutional atom jumps from one regular atomic site to the other by vacancy mechanism. This is called substitutional diffusion. So, for self diffusion or substitutional diffusion, this expression is valid. So, any atom, as we have seen, making a jump from its regular site into the next vacancy is equivalent to vacancy making a reverse jump. So, you can also consider diffusion of vacancy. Now, how the expression for D will be modified if we consider the diffusion of a vacancy? At any given temperature, the vacancy concentration is very low. We have seen close to melting point, the vacancy concentration is around 10 to power minus 4, the equilibrium vacancy concentration I am referring to, which means any vacancy will have only atoms as its nearest neighbors. The probability that a vacancy is on a nearest neighbor site to a vacancy is very low, right. So, at any given instance, a vacancy has 12 nearest neighbor sites onto which it can jump, unlike an atom can jump only if one of the nearest neighbor site is vacant. So, for vacancy diffusion, the second contribution is not required, or the second condition that the next site should be vacant is not required. So, the only barrier to the diffusion of vacancy comes because of the activation barrier for migration of the atom. So, for D vacancy, we will have D0 for vacancy exponential minus QD by RT. This is QD vacancy, and it has only contribution from delta HM. And in this D0 term, this delta S1V term will be absent. The only contribution to D0 in terms of entropy would be from entropy for migration. The similar equation will be valid for an interstitial diffusion, because an interstitial is occupying a void, it generates lot of strain within the crystal lattice. So, typically the equilibrium concentration of interstitial atoms is very low. For example, in FCC steel, maximum solubility of carbon is only 2%, whereas in BCC the maximum solubility is about 0.025%. So, that means that at any given instant an interstitial atom will have all its nearest neighbor site vacant. The probability that two nearest neighbor sites will be occupied by interstitial atoms is very low. And so, even for interstitial diffusion, the second condition is not required, the condition that the next site should be vacant, because most of the time any nearest neighbor site will be vacant. And so, the contribution to activation energy for diffusion of an interstitial atom is also only from the activation energy for migration of the interstitial atom. Of course, the activation energy for migration for the substitutional atom will not be same as that for the interstitial atom, but the only contribution is because of the activation barrier for migration for the interstitial atom. Okay. So, these are the two important mechanisms of diffusion, interstitial diffusion and substitutional diffusion in a metallic crystal. There are a few more mechanisms which were proposed. I will briefly mention those. One of them is called direct exchange. As the name suggests, it is a direct exchange between two atoms. So, if you consider atoms on their regular lattice sides, so let us say atom A and B here. In direct exchange mechanism, A will move to B, at the same time B will move to A. At the end of this exchange, the positions of A and B will be swapped. So, after the successful direct exchange, this will become A, this will become B. Now, you can imagine the activation barrier for this particular mechanism would be very high, because for this to happen, so many conditions have to be satisfied. The A has to gain enough energy, so that it can push apart all the neighboring atoms and move into B. At the same time, B has to gain enough energy, so that it can move into A. It is a very high energy process. So, this rarely occurs. So, even if the jumps of atoms are taking place by direct exchange mechanism, their net contribution to the diffusivity will be very, very low, because the activation energy would be very large. So, another mechanism which is referred to as ring mechanism. In this case, there will be minimum 3 atoms involved. Let us call this A, B, C, and in this they exchange their position among themselves in a ring fashion. So, in this case A will move to B, B will move to C, and C will move to A. So, after diffusion, the configuration will be A has moved to B, B has moved to C, and C has moved to A. Again, you can see the activation barrier for the ring mechanism would be very high, if you compare it with the vacancy mechanism. Right. So, the substitutional diffusion will most possibly and most easily will take place by vacancy mechanism. This type of mechanisms, which have very high activation barriers, will contribute insignificantly. Because of the high activation barrier, the probability of such jumps would be very low, and so the net contribution from these mechanisms will be very low. So, the most important mechanisms are vacancy mechanism for substitutional diffusion or self diffusion, and the interstitial mechanism for interstitial diffusion. Okay. So, we will stop here for today. Thank you.